All right, hey there, Pre-Al. Today we are starting our next chapter, which is functions and linear equations. If you take a look at the back wall, you'll notice this is our final of our Big Four standards. That does not mean that we're done after this, but it is our last one that we are going to introduce for our monthly checks, and one that we'll continue to practice over and over again for the rest of the year. And that starts with this idea, which is functions. So you can open up a blank page in your notes, and you can title that page Functions. Today we are going to start by just defining this idea of what is a function. So in your notes, and if you need to pause to keep up with this, that's totally okay. You're going to put the term function, and a function is defined by this idea that every domain or every x value is paired with exactly one range or one y value. So the way that I describe this to students sometimes is x's and y's are like boyfriends and girlfriends, and we don't want any of the x values to be cheating. So that means that the x values can only be paired with one y value. So for example, if we look at this table down here, okay, you can see that the value of 4 is only paired with 6. 7 is only with 10. 6 is only with 11. 3 is only with 8. 5 is only with 4. 2 is only with 9. So this is a function because each value is only paired with one y. Yes, this is a function. Now, if we look at this example here, what you'll notice as you look at this is the number 54 is with 112, and 54 is with 123. Okay, we also have 56 paired with 130 and with 128. So we've got two different x values here that are cheating. And they cannot be paired with more than one y value. So because 54 has more than one partner and 56 has more than one partner, no, this is not a function. All right. So each x can only have one y value. Now, the flip side of that, y values can be with as many x values as they want. They are terrible boyfriends and girlfriends. They are cheating all over the place. We don't really care about the y values when we look at functions. We only care about the x values. So we are looking to see, do the x's only have one partner? The y's can be with whoever. So an example of that might be something like this. Maybe we've got a table, x and y, that has 1, 2, 3, 4, and 5, and our y values are just this. Let's go 8, 8, 8, 8, and 8. All right. Now, you might immediately look at this and say, oh my gosh, there's a lot of cheating going on. This must not be a function. But if we think about this, for something to be a function, each x has to be with only one y. Well, 1 is only paired with 8. 2 is only paired with 8. 3 is only paired with 8. 4 is only paired with 8. And 5 is only paired with 8. So because each x only has one partner, yes, this is a function. So I like to use the relationship example because it's something that kind of sticks in your head. It's just a silly way to think about it. But we want those x's to be good in a relationship, good partners. So they can only be paired with one y value. The y's, we don't really care what they're doing, so we only look at the x's when we're using this rule. All right? Now, when we're looking at functions, we can look at functions in terms of graphs as well. And we have this really nifty way to figure out if something that is on a graph is a function, and it's what we call the vertical line test. And the vertical line test just tells us to run your pencil across your graph, as long as it only touches the graph at one place at a time, the graph is a function. Again, if you need to pause to copy that down, that is fine. But to do the vertical line test, we run your pencil across the graph. As long as it only touches the, oops, sorry, I forgot the word graph. Oh boy. The graph in one place at a time, then the graph is a function. So taking a look at these graphs down below. If I take my pencil and I run it across my graph, think about sliding that pencil from left to right. This is only going to touch this graph in one place at a time. So this is a function. Okay, my second example here, if I run my pencil across my graph, you can see this is only going to touch the graph one place at a time as we work across. So yes, this is a function. Now, what you'll notice on this third one, this is not a function because our pencil, as we run it across our graph, is touching in more than one place at a time. So if I look at this line or this pencil, it's touching that graph in two different spots. So no, this one is not a function. Similar idea here on the fourth one, right? Our pencil, as we run it across this graph, a bunch of times is going to touch in more than one spot at the same time. So that is not a function. These last two look to be good to me as I think about running that pencil across the graph. It's only touching in one place, one place, one place, one place. So yes, that is a function. Here, it's only touching in one place at a time, one place, one place. Yes, that is a function. So you can actually take your pencil and just kind of slide it across your iPad screen as you look at these and how each one of these is only touching that vertical line in one place. So this is kind of a quick little shortcut if you have the graph of a function to figure out, okay, is this a function or not, based on how many times that line crosses our vertical line or our pencil. All right, let's go ahead and move forward. This is kind of our last big piece of today's lesson, and it's this idea of function notation. All right, so in function notation, a lot of times what we'll see as we deal with equations is something like this, y equals 2x plus 3. Function notation uses this symbol, f with an x in parentheses. We would say this in words as f of x or function of x. And all that this is telling us is that this is a function, and we are going to be able to plug different numbers in place of the x to figure out what our function value or our function outcome will be at different spots. So let me show you an example. This one down below says f of x equals 4x minus 7. Find each function value. So part A asks me to evaluate my function at 5. So remember, what's normally in there is an x. This is asking me, what if that was a 5? So all I'm going to do is take my function, and instead of writing 4x minus 7, I'm going to substitute a 5 in place of that x. So when I solve this, 4 times 5 is 20. So my function at the value of 5 equals 13. That would be my answer. I can do the same thing over here on letter B. This one's asking me to evaluate the function at -6. So again, in place of the x, I'm going to put a -6. 4 times -6 is -24 minus 7. So my function evaluated at -6 is -31. And that is my answer. So all that we're doing when we evaluate function notation is plugging numbers in place of x and seeing what number comes out. If you think back to elementary school, when you were in like probably 3rd or 4th grade, you had those little things called function machines, right? They were drawn in your little math journals. They kind of looked like this, right? And you would have a function, like maybe it would say the number plus 5, and you would put in the number 10, and it would spit out the number 15. These were on those like little math boxes in your math journals, right? Well, all we're doing now is kind of the same idea, right? This example, our function was 4x minus 7. We're putting in 5, and we're getting out 13. Or we're putting in -6, and we're getting out -31. So the function notation is telling us what number goes into that function, and our job is to figure out what comes out after we do what the function tells us to do. All right, so moving ahead, we're going to take a look at these 5 examples. So what I want you to do now is pause the video, do these 5 examples in your notebook, and then press play again, and I will go over the answers with you. So go ahead and pause, try these 5, and then come back to the video. All right, so the first 2 just ask us, is this a function or not? 1a, I look at, are my x's being good in these relationships? So 5 is only with 1, 6 is only with 3, 7 is only with 5, and 8 is only with 0. So yes, this is a function. Each x value only has one partner. 1b, I'm looking for kind of the same thing, and what I notice is that my 1x is with 7 and with 8. Oh boy. So that means no, this one is not a function. Number 2 here, determine whether the graph is a function. So here's where we would use that vertical line test. And again, as I look at this, that's only hitting in one place. That's only hitting in one place. I'm going to keep going across, one place, one place. This line right here, whoops, looks like hits in 2 spots. I can also see a couple other places where this would hit in multiple spots at the same time. Here and here, here and here. So because of that, no, this is not a function. Our last piece here, asking us to evaluate the function 14 plus 3x at 2 different spots. So my first one, the function evaluated at 4. So I'm going to plug in 14 plus 3. Instead of x, we're putting a 4 in there. So that's 14 plus 12. So my function at 4 equals 26. My last one, same function, but this time we're plugging in -7. So I've got 14 plus 3 times -7, which is 14 plus -21. When I solve that or simplify that, my function at -7 is going to be -7. 14 minus 21 is -7. So those would be my answers. Hopefully that makes some sense. The rest of your time today is going to be practice problems. When I'm back tomorrow, I can answer any questions that you have on this, and we'll continue working through functions together. But the rest of your time today is going to be working on these problems, just the odds on page 402, 11 through 33. This is in Canvas with an answer key posted if you want to check as you work. And this will be due tomorrow. This is homework due tomorrow. And I think this video came in at just about 15 minutes, so this should leave you about 20 minutes to go ahead and work on this here in class and then finish up whatever you don't get done to hand in tomorrow. All right, the rest of the time is yours. Good luck. Have a great rest of your day. Bye.